This video is for section 13-7, Infinite Geometric Series. Take a look at these two example geometric series. 1, 2, 4, 8, 16, 32, 64, and so on. We can see that the value of r is 2. It's doubling from term to term. This series is going to increase without bound. Now look at the second one. 1, 1/2, 1/4, 1/8, and so on. This time the value of r is a half. You multiply each term by 1/2 to get the next term. The terms are getting smaller and smaller. They're converging at a value of 0. In the first series, the terms are diverging. They're getting larger and larger. They're not approaching a particular amount. One of these series we can find the sum of, and the other one we can't. If the absolute value of r is less than 1, then it's possible to sum the infinite series using this formula. Notice that you need to know the first term in the series and you need to know the value of r. On the other hand, if the absolute value of r is greater than 1, then you can't find the sum of the series. For instance, in that first example, the terms just keep getting larger and larger and larger. If you try to add them, you're not going to get a particular number. Let's try an example. For the infinite series in our two examples that it's possible to sum, find the sum. Well, that's going to be this second series. And let's use the formula. S equals, for the value of a, fill in the first term, and then 1 minus the value of r, and that was 1/2. So this is 1 over 1/2, which is equal to 2. If you added up this infinite amount of terms, the answer will be 2. Second example, find the sum of an infinite geometric series whose first term is 6 and whose ratio is 1/3. So we know the value of a and we know the value of r. And the absolute value of r equals 1/3 is less than 1. So it is possible to find this sum. Let's use the formula. S equals, now the first term, and then 1 minus the value of r. So this is 6 divided by 2/3, which is equivalent to 6 times 3 over 2, and that's equal to 9. Next example, use an infinite geometric series to determine the common fraction equivalent to this repeating decimal. So if you have 0.45, 45, 45, 45, and so on, what common fraction is equal to that? Here's the idea. 0.45 repeating is equal to 45 1/100ths plus 45 10,000ths plus 45 over 1,000,000, and so on. The 45 over 100 represents the 0.45 that's in the first two positions after the decimal dot. The 45 over 10,000 would represent a 45 in these two spots to the right of the decimal point. The 45 over 1,000,000 would represent having a 45 in these two spots. And if you add up 0.45 and 0.0045 and 0.000045, what you create is 0.45454545, and so on, as shown with this symbol with the line over top. This is an infinite geometric series. We can see that the first term right there is our value of a, and we can figure out what r is equal to. R is 1 over 100. Because you would multiply the first term by 1 over 100 to make this next term. And you would multiply the second term by 1 over 100 to make this term here. So we can find the sum using our formula. The value of a is 45 over 100. In the denominator, we have 1 minus the value of r. So this is 45 over 100 divided by 99 over 100. Now let's perform this division by changing to multiply. So we have 45 over 100 times 100 over 99. The 100s cross out, and we're left with 45 over 99. 45 over 99 is reducible because top and bottom both divide by 9, making 5 over 11. So the fraction 5/11ths is equivalent to the repeating decimal 0.45 repeating. Infinite geometric series is what creates our equivalencies between repeating decimals and fractions.